Good morning. In the last class, we had seen the classification of elementary particles and the related topics. Here we are continuing the topic with basic interactions, Higgs boson and LHC. So the first topic of discussion is basic interactions and field bosons. Interactions are also known as forces, so we can interpret it as basic forces also. So the basic forces and the field bosons. Field bosons are the particles that are exchanged when a force interacts between two particles. So field bosons are the exchanging particles. And there are basically four interactions or basic four forces are there. As you know, strong force, electromagnetic force, weak force and gravitational force. These are the four basic forces or interactions. We are going to compare these forces and we are going to see which are the particles affected by these forces, what is the range of these forces, what is the strength of these forces, and about the field bosons, that means the particle exchanged when this force is interacting between two particles. So that is the particles exchanged. And what is the role of this force or interaction in universe? So the first force is strong force. You know that the strong force is the nuclear force that exists inside the nucleus between the nucleons. And we know that the basic building block of matter as atoms, or we can say it as protons, neutrons and electrons. But these protons and neutrons are made up of quarks. You need not have to study about quarks more, but you have to know that quarks are the building blocks of hadrons. So hadrons are made up of quarks, and you know that hadrons are baryons plus mesons, and the proton and neutron come under baryons. So these protons and neutrons are made up of quarks. So the strong force is the force that exists between the nucleons inside the nucleus. And inside the nucleus, you know that there are protons and neutrons, and these are made up of quarks. So the particles affected by the strong force are quarks. And this strong force is experienced only inside the nucleus. So the radius of the nucleus is its range. That is approximately 10 raised to minus 15 meter. So the range of the strong force is 10 raised to minus 15 meter. And you know it is the strongest force. So we can give its relative strength as 1. We are giving it as 1 so that we can compare other forces with that of a strong force. Since a strong force is the strongest force, we are giving it as the strength 1. Now, which are the particles exchanged when strong force acts between the nucleons. I had already said that protons and neutrons are made up of quarks. So, whenever this quarks interacts with each other, some particles are exchanged and that particles are called gluons. The particles exchanged between the quarks in a proton or neutron is called gluons. So what is the role of this strong force or strong nuclear force? It will hold the quarks together to form nucleons. There are 6 types of quarks, and that are U, D, S, C, T and B. You don't need have to study that, but you have to know that there are 6 type of quarks and its antiquarks are there. So that proton is made up of 2 U quark and a D quark. That means the quark composition of proton is UUD. And neutron is made up of 2 D quark and 1 U quark. That means neutron is UDD. So these 3 quarks bind together so that a proton or a neutron is formed. So the role or the function of the strong force is to hold the quark together to form nucleons. Or we can say the particles affected by the strong force are hadrons. Generally we can say it as hadrons, but hadrons are made up of quarks. So when we say that the particles affected are hadrons, we can say that the exchanged particles are mesons. We are not going into the deeper concept of quarks. We are just saying that the particles affected are hadrons. So between the hadrons, mesons are exchanged. Mesons means we know the classification that mesons are classified into pions, kaons and eta mesons. So in meson family, the pions are the particles that get exchanged between the hadrons, so that the strong force holds nucleons together to form atomic nuclei. Either you can say about the it's a surface as a surface study like a hadrons and mesons, or you can go into the deeper concept of quarks, so that you can say the particles affected are quarks and the particles exchanged are gluons. So that's about the first basic interaction, which is the strongest of all interactions, that is strong force that exists between the nucleons in the nucleus. The second interaction is electromagnetic interaction. The electromagnetic interaction affects all the charged particles. So all the charged particles undergo electromagnetic interaction, and there is no particular range. That means its range is infinity. And the strength, you can see that the strength is given as 10 raised to minus 2, so that you can compare it with that of the strength of strong force. That means 1 by 10 raised to 2 forms 10 raised to minus 2. Now, if there is a force exists between two particles, there must be an exchanging particle between them, and that exchanging particle in the case of electromagnetic force is photons. Photons are massless particles that move with the velocity of light c, and it's having spin 1. Now this electromagnetic interaction determines the structures of atoms, molecules, solids and liquids also. It's an important factor in astronomical universe. So the next interaction is a weak interaction. Weak, as we had said in elementary particle classification, that leptons undergo weak interaction. So leptons and quarks undergo weak interaction with a range of 10 raised to minus 18 meter. Again, the quarks is there, that means the range will be inside the nucleus, so that, and the leptons include electrons, muons and tau particles. So the electrons are there outside the nucleus, and the nucleus is having radius 10 raised to minus 15 meter. So the electrons also gets interacted with the help of weak force. So the range is 10 raised to minus 18 meter. And its relative strength is 10 raised to minus 5, and the particles exchanged when weak force exists is intermediate bosons, which are also known as vector bosons, and it mediates the transformation of quarks and leptons, or helps to determine the composition of atomic nuclei. Since this weak force exists between the electrons, leptons and quarks, it helps to determine the composition of atomic nuclei. Now the last interaction, gravitational interaction, which is affected by all the particles and have infinite range. And the relative strength is 10 raised to minus 39, and when there exists a gravitational force between two particles, two masses, there will be a particle called graviton that got exchanged between these masses, and the graviton is a particle of a spin 2. So this is the gravitational force that assembles the matter into planets, stars and galaxies. So these are the 4 basic interactions or 4 basic force from which you can identify that the strong interaction is the strongest of all the forces, and gravitational as well as electromagnetic interaction have a range of infinity. Next you can see a picture that incorporates several branches of interaction. Here you can see electricity and magnetism that get joined together and form electromagnetic interaction. So initially, this is the list of fundamental interactions that has changed over the years. Initially, the long and weak interactions were unknown, and they thought that the gravity comes under 2 branches, like terrestrial gravity and astronomical gravity. Terrestrial gravity means the gravity that pulls the things down to the earth. So they called that gravity as terrestrial gravity. And they thought there is another gravity that holds the planets to their orbits around the sun, and they named it as astronomical gravity. But it was Newton who showed that both the terrestrial and astronomical gravity are the same. So here you can see the branches, terrestrial gravity and astronomical gravity. Since they are both are the same, they come under gravitational interaction. Electricity and magnetism, as you know that they are two different branches of physics, but it was Maxwell who showed that the electric and magnetic forces can traced or can be grouped to a single interaction between charged particles. So they together come under electromagnetic interaction. Later on, these electromagnetic and weak interactions turn out to be different branches of a single electroweak interaction. So now we have two interactions. On one side, gravitational interactions that joined together by terrestrial as well as astronomical gravity. And now we have electroweak interaction. Electroweak interaction means electromagnetic and weak interaction joined and form electroweak interaction. And the third interaction, that is a strong interaction. Here you can see that the strong interaction and electroweak interaction comes together to form grand unified interaction. But you can see that there is no gravitational interaction coming under grand unified interaction. So the physicists are trying to make a single picture of all the forces or interactions exist. So they are trying to unify all these interactions like gravitational interaction along with the grand unified interaction so that they come under a single interaction called universal interaction. So one of the goals of physics is a single theoretical picture that unites all the ways in which the particles of matter interact with each other. Much progress has been made, but still the task is not finished. So that's about the evolution of different forces or interactions in nature. So now the scientists are trying to make a single picture of all these forces through which the particles interact with the matter. So the unified, we had said that strong, weak, you can see that electroweak interaction and strong interaction come under grand unified interaction. So the strong, weak and electromagnetic interaction, the unified theory, their unified theory is what a standard model explains. So standard model explains a unified theory of strong, weak and electromagnetic interaction. There is no gravitational force exists in standard model. So in standard model, they considered world as built up of only two sets of particles. That are quarks and leptons. Quarks, the study of quarks is called quantum chromodynamics QCD. And you know that leptons undergo weak interaction, isn't it? And so the electromagnetic and weak theory comes for leptons. So the leptons are described by electroweak theory. So the standard model unifies the three basic interactions of a strong force, weak force and electromagnetic force. And in standard model, they consider there are two types of particles like leptons and quarks. Leptons described by electroweak theory and quarks described by quantum chromodynamics QCD. So standard model is trying to make a joint picture of both QCD and EW. And we had seen that universal interaction is there where we can join or we can combine all these four interactions. So that comes under grand unification theory, GUT. That is a unified theory explaining the four interactions. So we are giving more importance to standard model as well as grand unification theory. Since the standard model helped us to group strong interaction, weak interaction as well as electromagnetic interaction together. But the grand unification theory explains a unified theory of all the four basic interactions. From the standard model, Scottish physicist Peter Higgs said that a field must exist everywhere in space, and that field is called Higgs field. We know that when a charge exists, there is a region around a charge where other charges can experience a force of interaction, isn't it? And that region we named it as electric field, isn't it? Similar to that, there is a field that exists everywhere in space, and Peter Higgs named that field as Higgs field. So when particles move through this Higgs field or interacts with the Higgs field, they acquire their characteristic mass. So Peter Higgs said that the particles acquire mass when they move through this Higgs field. How? So this Higgs field exerts a kind of viscous drag on the particles that move through it. See, think of a particle which is moving through space, and according to Peter Higgs, the space is filled of Higgs field. So the particle is moving. Now the Higgs field is exerting like an opposing force to that particle. So it exerts a kind of viscous drag. You know that viscous drag, that is a force that opposes the motion of the particle, isn't it? So what happens when the particle moves through the Higgs field? This Higgs field exerts a kind of viscous drag on the particles, and this drag appears as inertia. And you know that according to Newton's first law, inertia defines the property of mass. Thus, the particle acquires mass. So when the particle interacts with the Higgs field, they acquire their characteristic mass. So the stronger the interaction, the greater will be the mass of the particle. So due to the presence of this Higgs field, a particle, so there is an interaction between Higgs field and particle, isn't it? So whenever there is an interaction, there must be a particle that get exchanged between them. That exchanging particle is called Higgs boson. Once again, for the standard model, we had said that the strong, weak and electromagnetic interactions come together under standard model. Or standard model explains the unified theory of strong, weak and electromagnetic interaction. So Peter Higgs said that there must be a field that exists everywhere in space, and that field is called Higgs field, and when particles move through that Higgs field, there is an interaction between the particle and Higgs field, so that Higgs field opposes the motion of the particle like that, a kind of a viscous drag, which appears as the inertia, or what we can say, it appears as the mass of the particle. So whenever there is an interaction between any two, there must be an exchanging particle between them, and that exchanging particle that mediates the action of the Higgs field is called Higgs boson. A particle called Higgs boson mediates the action of the Higgs field. So the scientist goes on searching the Higgs boson. So that Higgs boson, getting the identity of Higgs boson will prove Peter Higgs' concept of Higgs field, isn't it? So the scientists go for finding out this Higgs boson. So for that they had made LHC, or what we can say as Large Hadron Collider. It's a powerful accelerator. What is meant by accelerator? Accelerator is a device which accelerates the particle, or which increases the kinetic energy of the particle, isn't it? So LHC is the powerful accelerator we have now, and it's the world's largest and highest energy particle collider, or it's also the largest machine in the world, and it is placed, or it is at CERN in Switzerland, Geneva, and it's a circular, large, or we can say a huge circular tunnel, and this LHC is made for the discovery of Higgs boson and to know its mass and behavior as predicted by Standard Model. So from the Standard Model we had reached the concept of Higgs field and later on Higgs boson. So what Standard Model had predicted has to be experimentally discovered. For that, a Large Hadron Collider was made for the discovery of Higgs boson, and it started its working on 10th September 2008, and where you can see the protons, highly accelerated protons, are collided in a Large Hadron Collider. Highly accelerated protons are collided. See, when is it possible to collide two protons? Since the protons are positively charged, whenever they come together, what happens? They got repelled. So they are providing high energy to the protons, so that whenever they come each other, whenever they reach near, the high energy will overcome the repulsive force between the protons and they get collided. And whenever the protons get collided, there may be byproducts are formed, and by analyzing these byproducts, they are trying to solve the problem of Higgs boson and Higgs field. So that's about the Large Hadron Collider. Can see a picture here, which is a circular tunnel, and there is an Atlas detector also there to detect the byproducts of this after this collision. It's another picture where you can see two arms for that the circular. From there, from one arm one proton will be coming, and from the other arm another proton will be coming with high energy. So the protons get into the circular tunnel and get and undergoes several paths, so that its energy increased and got collided, and the collision products are being analyzed, and the studies are going on. So that's all for today. Thank you.